Oh, incredible. Wow. Beautiful. Welcome, Kappa. Incredible. It's right, Kappa. It's very, very competitive. Wait, there's an ad? There's an ad. Oh no. How do I turn ads off? I can't. Is that like some kind of legal problem? Is it at least a DoorDash? Oh no, I hope that's not going to be a legal issue. Please. Alright, well, we should start. Oh yeah? Wait, yeah, what's happening, Kappa? Oh my god. Oh no. That's definitely a legal issue right there. Okay, I got... Oh no. Oh no. No. Oh no, no, no. Oh no. Okay, students, come on in. I got 3 things I gotta tell you about today. Why ideals, part 2. Answer number 2. There will be a third answer, eventually. So why ideals? Answer. Quotient, because quotient rings. And then I'm gonna do something else, which is show you some examples of ideals and quotient rings. And then I'll do a concrete proof, just for fun. Polynomial rings over fields are principal ideal domains. Okay. Just for practice and fun. Okay. Theoretical stuff. Why ideals? Remember, we're gonna work with commutative ring throughout. Because that's the kind of rings that we'll be concerned with for the rest of like the year. Okay. So why ideals? Okay, so remember that an ideal obeys 2 things. The subgroup and 2, it's closed under arbitrary multiplication. Got it? Okay. So now the question is, where do these conditions come up? Why are these conditions placed on us? Every definition in your math classes emerges out of a need, out of a necessity, from somewhere. Okay, so here's why. We're going to talk about the following theorem. Okay. So let's play the following thought experiment. Most important thought experiment. Hello, Crow. How's it going? Okay, so most important, very important. It's very important that you be able to replicate this thought experiment on your own. Okay. Suppose someone gives you actually, yeah. Suppose someone gives you a subgroup. Of course, that just means under addition. It's closed under addition and negation. A ring is only a group under addition. Okay? Okay. So, suppose you have a subgroup. Well, since R isn't, since this is abelian, the subgroup is automatically normal. There's not, conjugation is stupid in abelian groups. Yeah. A is normal. So you can make it's the set of cosets. And the way you add two cosets is according to the group law. Okay? So that's all real. That's not fake news. That's real. That's old news. That's an old thing. The thought experiment is... Okay, cool. The thought experiment is, what if we try to impose a multiplication structure on the quotient group? What if we try to naively, in the most simple-minded way, impose a multiplication structure? Thereby making it into a ring again. It's a question, I guess. Crow, teacher's pet, awesome. Good steal. Okay, this is the question. What if we try to do this? All right? And the answer, so the outcome, the answer of this question you must require A to be an ideal. That's where the concept is born. That's the reason we isolate this second condition. It's clear that this second condition is, you have questions. Why? Why do we do this? All right? And that's where it's coming in. So let's state it as a theorem. Okay, so, or a proposition. I'm going to do it one way. I'm going to do first direction. If A is an ideal, then the rule, this coset star this coset equals, by definition, this coset, this star multiplication rule is well defined. It's saying that this is a real operation. That the computer will parse this if A is an ideal. Okay, so I need to now, we're going to prove this. I just need you to remember something about how cosets work when you take in quotient group. Just for us, recall. Refresher. One coset is equal to another. Right? These two are equal. Maybe I should use different symbols. X and Y. These two cosets are equal if and only if X times, okay, X group law Y inverse is in the subgroup. All right? So that's something to remember. That's how you know when you're talking about the same coset or not. The representatives differ by an element in A or not. Great. Just recall that, how cosets worked. Okay, so what do you have to prove? How do you show something is well defined? Okay, so what you do is you suppose this coset is also this one. You pretend you gave two separate names to the same coset. You pretend you chose two separate representatives for the same coset. And suppose coset S is the same as coset S prime. We need to show that the star operation outputs the same coset. I.e., that, read the operation, the recipe. You put this representative and that representative, you multiply them, and you create a representative out of that. Make that coset. We're asking, we need to check this. That's the whole content of the theorem. Two cosets are the same. Okay. How do you check that two cosets are the same? You do this. So maybe we should look at R prime S prime minus RS. Okay. So R plus A equals R prime plus A is the same as saying R minus R prime is an element in the subset, in the subgroup. And this is the same as saying S minus S prime is an element in the subgroup that we're quotienting by. Okay? Great. So now I'm going to put this stuff, I'm going to follow my nose here. Okay, so now computation. R prime S prime is R plus A times S plus B, which is RS plus AS. Remember, this is in plus RB, like arbitrary, plus AB. But pay attention. assumption. A is an ideal. Gives that AS is in A again. And RB is in A. And of course, A times B is in A. So, R prime S prime is RS plus something in A. A is closed under addition. All three of these are in A, thanks to my assumption that A is an ideal. Notice, if you're thinking, wow, what about the non-commutative world? Notice that I need A to be both a left ideal and a right ideal at this critical juncture. See, look. S is multiplying on the right here. I need to know that that's in A again. And R is multiplying on the left here. I need to know that that's in A again. That's where the two-sided ideal comes in whenever you read non-commutative ring theory. Okay, but anyway, we're here. We're home. R prime, S prime, and RS represent the same coset. All right? So the star operation, the naive, simple-minded star operation makes sense. Makes sense. It is allowable. It is not a contradiction in terms. Okay. All right. So, that's one half of why being an ideal is important. That multiplication rule is inherited by the quotient group. Okay. So, students can check if A is an ideal. I'm going to start using I. If I is an ideal, then R mod I with coset addition and coset multiplication, which we can only talk about thanks to the idealness that this is a ring again. It's called the quotient ring. And the book calls it the factor ring. Don't call it that. Don't call it the factor ring. That's some boomer stuff. Don't do that. Okay? Quotient ring. All right? I'll tell you what there's a one element. A lot of times people start using the symbol for the quotient, for the coset R plus I, you can use R with a bar on top. Or you can use this. Okay? So what is the one in, it's a ring. It's a ring. I said it's a ring, not a rung. All right, what is it? It's the coset 1 plus I. You don't believe me? Look, do the... It's stupid, yeah? Okay, good. Great. What's the additive identity? 0 plus I. I itself. Okay, so now, the opposite direction. Opposite direction. What if A inside of R is a subgroup which is not an ideal. So the second condition is failing. i.e., what if there exists an element in here and an element in the ring such that R times A was not in here? Okay, check out the following contradiction. Star would get broken. Then answer. Star gets messed up. Because what you look at is the following multiplication. The following star calculation. Well, according to the rules say this is A times R coset. Okay, but according to cosets, this is the coset 0 plus A. These are the same coset. That's the trivial coset. So I come back tomorrow and I call it what it actually is, 0 plus A. And I do star. I do the star recipe. And I get 0 times R plus A. Namely, 0 plus A. And now the issue is, these are not the same because RA is not an element in A. Or AR. We're commutative. Commutative. And so, star is broken. Star is not well defined. Bad equals... Oh, I get it now. Being an ideal is a necessary and sufficient condition for the multiplication rule to descend to the quotient. Okay, so that's the critical thing. That's what I'm talking about. All right, that's my second answer to why an ideal. Now I'm going to show you some examples right away now. That was the second thing I wanted to do. Examples. Okay, of course, the first example is Z mod NZ. That's an ideal. All multiples of n. It's the principal ideal generated by the integer n. Beautiful. Okay. Then what is Z mod NZ? It's the set of left and right cosets are the same. We're in an abelian group, folks. It's a set of cosets of NZ. Okay? This is 0 plus nz. It starts with, yeah? And how do you multiply two of them? Adding them, you already know. How do you multiply two of them? Like that. And you might be able to rewrite this coset as with a different representative. That's up to you. That's up to you. But it's just this. So for example, n equals 6. Then 3 plus 6z times 2 plus 6z equals no, 4 equals 12 plus 6z. But 12 plus 6z is the same coset as 0 plus 6z. We're not saying 12 is the same number as 0. We're saying its coset is the same as 0's coset. That's a true statement. Everything we're saying is just 100% on the nose true. We're not equivocating between concepts. We are working with cosets, not with integers themselves. Okay? And so modular arithmetic is set on firm foundation right here, after the great proposition of y ideals. Great. Okay. So, a second example. Okay. This kind of example, super important as we move forward. All of next semester is the study of this kind of an example. All right, so this example, like 90% of next semester. That's right. There's a whole class built on these kinds of examples. Ready? I'm going to start with a ring. Real polynomials, one variable. Polynomial ring over the with real coefficients. Polynomials with real coefficients. Now let's look at the following ideal. In life, folks, how do you specify an ideal? For us right now, we have one tool. Principal ideal. Pick an element, take all multiples. All multiples of the polynomial t squared plus 1. Okay, let me write that out. Okay, I'm now going to investigate what quotienting by I feels like. What ring do we get? First of all, it's a ring. We just learned that 15 minutes ago. It's a ring. No, you can't deny that. But what does it feel like? What does it feel like to do mathematics in this ring? Let's go just by the definitions. All right. We're going to need to write down all the cosets of I. Okay, what are the cosets? 1. But do we know it? Okay, so step 1. Let's try to get clarity on all the cosets. Let's think about it. Let me show you the claim, and then you'll be able to reverse justify it. Okay, here's the claim. The set of cosets are in bijection with the following types of polynomials. And the bijection is a simple one. That if I give you a plus bt, you just write down that coset. Okay, plus the ideal generated by maybe I should write I everywhere. Okay? And I'm claiming that this is a bijection, this map. Okay, so let's look. Write any coset. Write any coset. Go ahead and write any coset. Oh, it's going to be some huge polynomial. Plus the ideal I. But now, I'm going to ask you to do something. Take that coset representative and do division with remainder. By what? By t squared plus 1. Do long division. You're going to get some polynomial plus a remainder polynomial. And the remainder has degree smaller than 2. But what does this buy us? Why is this important? Because if you know this division with remainder fact, which you should from elementary school, then this coset is the same as this coset. After all, the difference is an element in the ideal. It's a multiple of t squared plus 1. So, every coset can be written as a linear polynomial plus the ideal. Okay, and students, I want you to check that if you take two different linear polynomials, they will have to be different cosets. Okay, so the cosets are exactly labeled by linear polynomials in T, a plus bt. All right, so now 3. How do you add two cosets? Well, the addition rule is just coset addition. That's how you add in the quotient group. How do you multiply two of them? Pay attention. How do you multiply two of them? multiply the representatives. Foil. And now the question is, which coset is this when you label every coset by a linear polynomial only? Notice right now, our representative is a quadratic polynomial. There's no rules against that, but if we want to see which coset it is in our one list of all cosets, where we listed every coset by a linear expression, we got to do some reduction. So look, you'll get AC plus BC plus AD times T plus BD times T squared plus I. Hold on. What we know that T squared plus 1 is in I. Obviously, T squared, the element. Obviously. So BD and so pay attention. That means that these two cosets are the same. These are the same coset. And so I can reduce my expression. I get AC minus BD plus BC plus AD T. All right, look carefully. I multiplied A plus BT, C plus DT, the cosets, and I ended up with the coset whose name is this linear polynomial plus I. All right? And if you stare at that, you will feel in your bones that you are doing mathematics in the complex numbers. And that A plus BT is the same as A plus BI. This coset is A plus BI. All right? So what's the punchline of this example? Very important example. C, which you might have thought, oh, it's some imaginary thing. You make up some new math. You just, very, very delicate thing. You just make up I and you put it perpendicular and you sort of visualize it like this. And multiplication is rotation and angle and cosine theta, sine theta, all this. No. C is a quotient ring. No, sorry. What are you? It's just a quotient ring. What are you talking about? In a sense. We've placed this in the same footing, same algebraic construction as Z mod 6Z. Just a quotient ring. Took an original ring, in fact, modded out by an ideal. C can be obtained as the same way. Okay? Great. And very important that you realize that some of them, these rings or fields that had their own PR apparatus, pop culture, pop sci magazine will write entire articles about how crazy they are. It's one quotient. One quotient. How many articles can we write now? We can write billions and trillions of articles now because we can take quotients and do bizarre math. Extend the concept of a number. Yeah, quotient. Do quotients. We can make hundreds and hundreds of dollars now by writing pop sci articles about what a bizarre thing we're doing. Just a quotient by an ideal. But our playground is now enormous, as we will see. Okay, great. That's why quotients are great. Some examples of quotients. And now I'm going to move on. Okay. That's right, algebraically challenged. That's right. T squared plus 1 is maximal. The maximal ideal. Great. Okay. What was I going to talk about last? Oh yeah, last thing. Yeah. I was going to do this. Just for kicks. Just for kicks. If F is a field, kicks. So you get practice seeing a proof using in a polynomial ring. If F is a field, and if then all right, I want to show you this. I want to show you this real fast because it illustrates the importance of this concept that you can use to your advantage when dealing with a polynomial ring in one variable. Okay, so the degree. Every time we write a polynomial out like this, it's always assumed, unless they specify otherwise, that the top coefficient is non-zero. Because why did they write it otherwise? Jude, what happened? Okay, if you have a polynomial, then its degree is this number. That's the concept of a degree, right? We write degree if this is a of t. Degree of a of t. It is a measurement of bigness of a polynomial. And what's important about the polynomial ring and this notion of degree is the division with remainder theorem. Suppose A is a non-zero polynomial. And B is any polynomial. Then there is a unique. Then there are unique polynomials Q of t and R of t such that B is is that Q times A plus R, first of all. Secondly, degree of R is strictly less than the degree of A. Division with remainder yields essentially a unique quotient and remainder polynomial. They are sort of... that apparatus works. And the proof? This is something you should have done in 3613, maybe. Proof is long division. Like this. You'll get a remainder exactly when all the subtractions and stuff yields a polynomial of degree smaller than A. All right? And it's very important that we work over a field, because when you do long division, what do? You look at the highest degree part and you multiply so that you can achieve it. But you're going to have to be able to divide by the constants in order to match it perfectly. See, look, you're going to have to write eight over 3. You need to do 3 inverse in order to make the long division procedure even go, okay? That's why F being a field is absolutely needed in this, to make long division a thing, all right? So once you have that ability, you can prove this very, very simply. And now, the last thing I want to say today is, how does this thing go? The proof for Z follows word for word, except now you need to argue with choose a polynomial of smallest degree inside a given ideal. The first sentence instead instead of this, you do this. and then follow the proof. I believe in you. Okay? So this concept of degree is kind of analogous to this concept of raw size of an integer. They play a parallel role, and they yield similar theorems for the polynomial ring in one variable and for the integers on the other side. Okay? So that's, I want you to go finish that proof. I've given you the main ingredient, division algorithm. Okay. Let's wrap up. Let's start rolling the credits. I invented the concept of credits on Twitch, apparently. Is Hang's mate in one here? Yes, they can verify. Okay, so who are the teacher's pets? Kappa was. Kappa. And then Crow. Did it again. All right. On purpose. Yeah. No, actually, while I was dragging the box, that's when I realized. And I was like, whatever. It's just, whatever. What did Hank's mate in one? Hank's mate in one, calling out the racists. Yeah. Awesome. Thank you. Thank you for doing that. Thank you. What else happened? Oh, AC. Mod. Okay, keeping chat in check. Okay, Vixen. Vixen's here. Okay, what did Vixen do? Okay, Vixen. DoorDash. Do tell. Ha 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 ha. Okay, good. Yeah. Okay. Who else was here? Itasuk. Who else was here? Which other students were here? I'm sure they were all here. They just kind of chill. RDL was probably here. Sloth was probably here. All my students. All of you. Okay. Who is this XYZ panda? Lol, I don't know what any of this is. How many guys are following the lesson? There's more than... Okay, can actually understand what he's talking about. Actually, I think all of them. Because this course has been going for a while, Panda. Dr. K's distant cousin. Ah. Okay, I guess Panda. New friend. This doesn't look like the normal gibberish. Wait, Kappa is unhinged? Okay. Oh my god, Kappa. What is that? What is that? Oh boy. Oh boy. uh... Linear algebra is a part of abstract algebra. Absolutely. 100%. It is a special case of studying modules over a ring. Okay, this is good. This is good enough. Yeah, Kappa, you're gonna get banned. How do I ban Kappa? How do I ban for like 1 second? Oh, we need to, yeah. Good point. Good point, Hangsmate in one. We need to thank the concept of ideals. Hey, ideals, thank you for allowing us to quotient by you, thereby exploding our list of rings that we can create. It's not just Z and then Z adjoin X, Z adjoin X and Y. No, way more. Take a ring, mod out by an ideal. New ring. Which one is it? If the stars align, maybe you can recognize it in your list again. But most likely, just a new ring. All right. Okay. Kappa, is there something to be said about the fact that a quotient has to be a unitary ring, even if we start with a rung? No, even if you start with the rung, the quotient will still be a rung. All right? But it typically won't be a ring. Yeah, typically won't be a ring. Okay. But I told you, if you start with a ring, the quotient is a ring. Because the coset 1 bar is the new unit, the new multiplicative identity. Great. Okay. Okay, so what do I have to do now? I have to learn power series. Okay, so here's the credits. Here you go. Yeah, Kappa, everything I said today about building a quotient object works for rungs too. And it works for arbitrary rings as long as the ideal is two-sided. Anyway, whatever. Okay, so I guess I'll go learn about what is a power series? What is it? I don't know. And then I'll have to teach that subject. Is there anyone, I don't know, is educator on? Any educators on? Like Professor Peter? I want to raid Professor Peter. Oh, Professor Peter's on. That's right. Okay, Hangsmate. Okay, good. So you're gonna go in there and you're gonna say, Quotient gang. Quotient gang. Alright? He won't have BMP's emotes activated. No one does. I've asked every person, hey, can you go and activate the BMP emotes? And all responses were just no. So your emotes won't work over there. Okay, just say quotient gang. All right, here we go. Here we go.
Aren't